Okay, so today we're going to finish our discussion of moment-generating functions and get a quick introduction to characteristic functions, and then we're done. So, moment-generating functions, as we'll recall, as you'll recall from Tuesday's lecture, it's possible for moments not to exist. That the way moments are defined, you have to have the expected value of x to the rth power be finite. If it's not finite, then by definition the moment does not exist. So, in general, if any particular moments of a random variable do not exist, then the moment generating function doesn't exist either. That you can show if you calculate logs and so forth that in general e to the power of tx will always be greater than or equal to e expected value of x to the r times c for an appropriately large c. So that implies that if any of those moments are infinite, then the expectation that you need for the moment generating function will also be infinite and the moment generating function won't exist. So in particular, for the Cauchy distribution, no moments exist, the moment generating function does not exist. And it's possible even for there to be distributions where the moments exist, but the moment generating function still does not exist. The canonical example of this one is the log normal distribution, where you'll recall if x is normal and if you let y equals e to the x, then y is log normal with the distribution function listed below. And you can show that for this distribution all the moments exist, but the integral expected value of e to the ty doesn't converge, and hence the moment generating function does not exist. So, but you can prove, as I'll show here in a second, that if the moment generating function exists, then all moments exist. That, as I noted before, if you fix some value of p around the origin, you can show that there exists some c such that e to the tx will be greater than or equal to x to the r for all real numbers. I won't go through the details of the proof. The easiest way to see is if you just take logs of both sides and simplify the expression. You can find an expression for c such that that will be true for all x. So that implies that the expected value of x to the r power for any r is going to be less than or equal to some constant times the expected value of e to the tx, which of course you can just write as expected value of e to the tx plus expected value of e to the minus tx, which is just the moment generating function evaluated at t and minus t, which, if the moment generating function exists, that's finite, implies that all the moments are finite. And as I said before, one of the main reasons why we care about moment generating functions as well as characteristic functions, as we'll talk about here in a second, is that under some circumstances they can characterize the distributions. That if a random variable has unbounded support, that is, if it can take, if it has positive probability, either positive probability mass or positive probability density, on a series of values that increases or decreases without bound. I mean, the intuition is that if you graph the density function, the graph goes all the way out to infinity, whereas bounded support means that it's zero after a certain cutoff. If the support is unbounded, you can find distributions with different PDFs that have all the same moments. There's an example in Cassell and Berger if you're curious about that. But if the support is bounded, then the moments do uniquely specify the distribution. But more importantly, moment generating functions will uniquely identify distributions provided that the moment generating functions exist. And we can state this formally in terms of a theorem. If you let x and y be some distributions that have CDFs and all their moments exist, if x and y have bounded support, then if all the moments are the same, that implies that they have the same distribution, and likewise they have the same distribution. That implies that all the moments are the same. The bounded support condition is necessary for this, though. It means that it can only take on that the range of values for which the density or mass of the function is positive is bounded. So, I mean, maybe it'll be easier to see by examples. Like the binomial distribution, you flip a coin 10 times, count the number of heads. That would have bounded support because it assumes a range between 0 and 10, which is a bounded range. But something like the negative binomial distribution, which you keep flipping a coin until you get a heads and then you stop, that would not have bounded support because in theory you could have 1,000,000 or 10,000,000 or 10 Googleplex tails before you get the first head. So there's no bound on the possible range of values for x. Likewise, the normal distribution, I mean most continuous distributions that we care about don't have bounded support because they can assume any value between minus infinity and infinity. I think the one continuous distribution that we've discussed that does have bounded support would be like the uniform distribution on 0 to 1. It can only take on values between 0 and 1, so its support's bounded. Does that make sense?
Is there a distinction between like having a bound on one side? So for instance, something that goes from 0 to infinity?
That would still be unbound support in this case. I mean, it's bounded on only one side. But for this theorem to apply, you have to have bounds both above and below. If the support's unbounded, then in general that condition won't be, that theorem there won't be true. But the more important part of this theorem at any rate is the second part, that if the moment generating functions exist and they're equal to one another for some t around 0, that implies that the two distributions are the same. Among other things, like I said, this is used to prove the central limit theorem, that you show that for a large class of distributions that their moment generating functions converge to the moment generating function of a standard normal. That implies that when you take the mean of a bunch of things, it becomes normal.
For number 2, do we also need the condition that x and y are
No. And the other important reason that we care about moment generating functions is because if the moment generating functions converge, that implies that the CDFs and hence the distributions themselves converge. That more formally, say you have a sequence of random variables with moment generating functions mx1, mx2, such that the limit as n goes to infinity of the mxn's converges to some moment generating function. Then there's some unique CDF whose moments are given by this particular moment generating function, and where this f is continuous such that the limit of the series of CDFs is precisely this f. And like I said, that's what gives you the central limit theorem among other things. So proof of the central limit theorem, I mean, I don't know if we get into that in this class at all. I'm sure you'll see it at some point in your career. But just to give one example of how you can use the moment generating function to prove that things become normal for large sample sizes, let's just look at the normal approximation to the Poisson distribution. Can't remember if I've discussed the Poisson distribution before. We'll be discussing it in much more detail here in a week or two regardless. But one way or another, the Poisson distribution, if you calculate its moment generating function, it looks like that. There's an exercise in Cassel and Berger where it'll ask you to calculate this. In particular, its expected value and variance are both equal to its rate parameter lambda. So let's subtract the mean and divide by the standard deviation, the standard normalization trick when you're dealing with things that are likely to be normal. And so define this random variable y to be x minus the mean divided by the square root of the variance. In other words, x minus lambda divided by the square root of lambda. So if you recall the formula for the moment generating function of a defined transformation from Tuesday's lecture, that will just be, in general, the expression is e to, if y equals ax plus b, then the moment generating function of that transformed variable will be e to the bt times the moment generating function of at. So in this case, b would be minus lambda divided by the square root of lambda, which is just the square root of lambda. So e to the minus bt would be e to the minus square root of lambda t times the moment generated function of x evaluated at t divided by lambda. So the easiest way to figure out what that will converge to as lambda becomes large is to take the log of this moment generating function, which of course will just be equal to minus t times the square root of lambda plus lambda times e to the t over the square root of lambda minus 1. So now let's take the Taylor series expansion of e to the t lambda. That'll be 1 plus t over the square root of lambda plus t over the square root of lambda squared times 2 factorial or plus 1 over 3 factorial times t over the square root of lambda to the third power, etc., up to that infinite sum. So we multiply that out, and the first two terms, and the lambda times t over the square root of lambda will end up being precisely t times lambda. So it will, the pointer's not being very happy today, will cancel with the minus t to the lambda. The second term will end, the lambda will cancel with the lambda in the denominator there. We end up with t squared over 2. Then we end up with t cubed over 3 factorial times lambda to the 1/2, plus a bunch of other terms, all of which will have lambda in the denominator. So as lambda goes to infinity, t squared over 2 will stay t squared over 2, but everything that has lambda in the denominator will go to 0. So that gives us that the limit as lambda goes to infinity of this moment generating function in terms of this new variable y is just e to the t squared over 2, which, as you'll recall, is precisely the moment generating function of a normal random variable with mean 0 and standard deviation 1. So we've just proven that if you have a Poisson random variable and let its rate parameter become large, it becomes approximately normal. And like I say, to prove the central limit theorem, you do essentially the same argument, just in much more generality. And quick aside, if you've ever taken a bunch of math or engineering classes, you may have heard of the Laplace transform. the moment generating function is closely related to the two-sided Laplace transform. But, I mean, as I recall, the exponent is slightly different, but it's the same basic idea. If you have a table of two-sided Laplace transforms, it can help you find the moment generating functions of certain things. And you can also talk about something called the cumulant generating function, which is defined to be the log of the moment generating function that, and the derivatives at t equals 0 are called cumulants. And in particular, the first derivative evaluated at 0 is the expected value, and the second derivative evaluated at 0 is precisely equal to the variance. And I think like the third and fourth cumulants have something to do with the skewness and kurtosis, but I honestly don't remember, and I don't think I've ever used these cumulant generating functions before in my life, to be honest, so don't waste too many brain cells on them. Well, there's an example of the cumulant generating function of the normal distribution. Okay, now characteristic functions. Characteristic function is closely related to the moment generating function, that rather than taking e to the tx, you take e to the I times t times x, where hopefully you've seen imaginary numbers before. I squared is just the square root of -1. And if you have seen these things before and have taken some more advanced courses, you might recognize that you can show that e to the itx is always equal to cosine of tx plus I times the sine of tx. That you can prove that pretty easily just using like the sine squared plus cosine squared equals 1 identity. If you haven't seen it before, you can just take my word for it. And properties of the characteristic function, obviously, it's complex valued. Since it has an I in the exponent, it will have both real and imaginary parts in general. And one big advantage over the characteristic function over the moment generating function is that it always exists. As you can see here, the absolute value of the expected value, and I should fix that because that's technically wrong. The person that I got the slides from did not know the correct definition of when the expected value exists, and I fixed this elsewhere, but I overlooked it here. Actually, all we need to show is this piece. He wanted to show that the absolute value of the expectation is finite, but that's wrong. To prove that a moment exists, you have to show that the expectation of the absolute value is finite. So I will try to fix this and upload an updated version of these lecture slides. But expected value of e to the itx by this expression up here, if you square that, it's precisely equal to 1. So this expectation is always less than or equal to 1, so it always exists and is finite. And generally speaking, to calculate the characteristic function, you can usually just take the moment generating function and replace I times t with t everywhere you see it, and then you have the characteristic function, assuming that the moment generating function exists. And this second property here is the main reason to care about characteristic functions, because they will exist even if the moment generating function doesn't exist. That, like I said, one of the probably the most important example of where you would use moment generating functions or characteristic functions is to prove the central limit theorem. And you can prove the central limit theorem using moment generating functions. The problem with that is, as I just said, the moment generating function will only exist if all moments exist, and that's a very strong assumption. And it turns out the central limit theorem doesn't require assumptions that strong. In general, you only need the first two moments to exist. If the mean and variance are finite, but all the higher order moments are infinite, the central limit theorem still applies. But you couldn't prove that using moment generating functions. You can prove that using characteristic functions. So that's the reason why we care about this sort of thing. So, examples of characteristic functions, I won't go through the details of most of these because, as I said, if you know the moment generating function, you just take every t that you see in the moment generating function, replace it with I times t, and then you've got the characteristic function. So, as you'll recall, moment generating function for the exponential was lambda over lambda minus t. The characteristic function is lambda over lambda minus it. Similarly, the characteristic function of the normal distribution is e to the I times mu times t minus sigma squared t squared over 2. In this case, note that I squared is minus 1, so when you take I times t squared, you just end up with t squared times minus 1, so this plus changes to a minus, and the I disappears. For geometric random variable, again, just every place that we see e to the t, we replace with e to the it, so it's p times e to the it over 1 minus q times e to the it. And since this expectation is always finite, the characteristic function is always defined for all t. You'll recall the moment generating function, we only required it to be finite for some t near 0. We don't even have to worry about that condition with characteristic functions because it's always finite for all t in every single case. And I won't go through the details of the math, but the characteristic function of the Cauchy distribution exists if you take the integral from minus infinity to infinity of e to the itx, and it involves some ugly trig and stuff, but if once the smoke clears, you end up with e to the minus absolute value of t. So the Cauchy distribution has a characteristic function, even though it does not have a moment generating function. As I said, every distribution has a characteristic function. Some other properties of the characteristic function, as I said before, the absolute value of the characteristic function for any t is always less than or equal to the characteristic function evaluated at 0, which is of course equal to 1. Oh, the absolute value of the characteristic function will be less than or equal to 1 for all possible values of t. And it's pretty easy to show, or so there will be a homework problem on this later, that the complex conjugate of the characteristic function can be obtained by just replacing t with minus t in the expression for the characteristic function. And the same trick that we use to find linear transformations of the moment generating function also works for the characteristic function. You just take e to the ibt times the characteristic function evaluated at a times t. And one property that's kind of cool and convenient sometimes is that a distribution is symmetric around 0 if and only if the characteristic function is real valued. That's also quite easy to prove, that if it's symmetric, the imaginary part will always cancel out. And you can calculate moments using the characteristic function just like you can for the characteristic function, that you just differentiate n times and evaluate it at 0. And I don't think this expression is strictly correct, because for the characteristic function you have an I to the n times the nth moment, which you won't have if you use the moment generating function. I'll try to remember to fix that as well, but no big deal, you get the idea. And characteristic functions will also uniquely identify distributions, just like in the case of moment generating functions, that if you have two characteristic functions that are equal to one another for all t, then the CDFs associated with those characteristic functions are the same, and hence they have the same distribution. And the same property about convergent sequences of random variables that I described for moment generating functions also works for characteristic functions, that if you have a series of random variables whose characteristic function converges to something, then that implies that the distribution the distribution of those random variables is converging to whatever that characteristic function is. Like I said, this is how you prove the central limit theorem. You show that the characteristic functions converge of a very large collection of random variables under suitable conditions converges to the characteristic function of a standard normal. That implies when you average a bunch of stuff together, you get something that's normal. And a couple final quick asides that for continuous random variables, the characteristic function is very similar to the Fourier transformation of that particular function. Again, I think this is used more in engineering than it is in statistics or math, but this is kind of a handy thing that if you ever need to, if you want to look up the characteristic function, for trying to calculate the characteristic function of something and it's an ugly integral that you don't want to calculate, if you find a table of Fourier transformations, oftentimes you will have it calculated for you without having to explode your head doing ugly integrals. And yeah, I guess I was right that this lecture turned out to be really short. Any questions about any of this? Okay, as I said, for the 690 students, I was going to do another discussion section during the rest of the time. Just briefly talk about the stuff I posted last night on continuity and differentiability. If you're an MS student, feel free to leave, but it's likely that even the discussion section that I prepared probably will not go for very long. There should be some downtime if people want to stay for homework questions or whatever. If not, then feel free to go home or go somewhere and wait for seminar to start, as the case may be.